Before we drift into the 100 sleepy facts, imagine yourself lying beneath a velvet night sky. The world quiets. The stars shimmer gently. And up above, stretching across space like a river of ancient light, the Milky Way whispers stories older than Earth itself. Tonight, we follow that whisper. Slowly. Calmly. Comfortably. Let the galaxy cradle your thoughts as we wander through its mysteries. Fact 1. A river of stars in the night sky. When you look up on a clear, dark night, you might see a faint band of light stretching across the heavens like spilled milk. This is how our galaxy got its name, the Milky Way. Ancient Greek storytellers called it Galaxias Kyklos, meaning milky circle, and civilizations around the world saw it as a celestial river, a path of souls, or a bridge between worlds. What you're actually seeing is our view from inside the galaxy itself, looking through the disk of billions upon billions of stars. Fact 2. Our island universe. The Milky Way is what astronomers call a barred spiral galaxy, one of hundreds of billions of galaxies floating through the cosmos. Imagine a spinning pinwheel of stars, gas, and dust, with graceful spiral arms curving outward from a central bar of stars. Our galaxy is home to somewhere between 100 billion and 400 billion stars, though the exact number remains uncertain because so much of the galaxy is hidden behind dust and distance. Fact 3. A vast cosmic disk. If you could somehow travel to the edge of our galaxy at the speed of light, it would take you about 50,000 years to reach the outer rim from where our sun resides. The Milky Way stretches approximately 100,000 to 200,000 light-years from edge to edge, making it a truly vast cosmic structure. Yet despite containing hundreds of billions of stars, the galaxy is mostly empty space, with vast distances between each point of light. Fact 4. Our galactic address. Our sun doesn't reside in any particularly special location within the Milky Way. Instead, we make our home in what astronomers call the Orion Arm, sometimes known as the Orion Spur, a minor spiral arm located about 26,000 light-years from the galactic center. Think of it as living in the suburbs of our galaxy, far from the crowded downtown core but not quite in the distant outskirts. Fact 5. A rotating cosmic carousel. The Milky Way doesn't stand still in space. Instead, it rotates majestically, though not like a solid wheel. Our Sun and Solar System are orbiting the galactic center at a speed of about 515,000 miles per hour, yet even at this tremendous velocity, it takes approximately 225 to 250 million years to complete one orbit around the galaxy. This orbital period is sometimes called a cosmic year or galactic year. Fact 6. Ancient travelers around the galaxy. Since the Sun and Earth formed about 4.6 billion years ago, our solar system has made roughly 20 trips around the galactic center. When dinosaurs walked the Earth during the Mesozoic era, our solar system was in a different part of the galaxy entirely. The last time we were in our current galactic position, small mammals were just beginning to diversify after the extinction of the dinosaurs. Fact 7. The galactic disk's slim profile. While the Milky Way stretches for tens of thousands of light-years across, it's remarkably thin in comparison. The main disk of stars where most of the galaxy's stellar population resides is only about 1,000 light-years thick in most places. If you were to scale the galaxy down to the size of a dinner plate, the disk would be about as thin as a crepe or a sheet of paper. Fact 8. The galactic bulge at the center. At the heart of our galaxy lies a densely packed region called the galactic bulge, where stars crowd together much more tightly than in our neighborhood. This central bulge extends roughly 10,000 light-years from the galactic core and contains some of the oldest stars in the Milky Way, many of them over 10 billion years old. These ancient suns formed when our galaxy was still young and have witnessed nearly the entire history of the Milky Way. Fact 9. Hidden by dust and gas. Much of the inner Milky Way remains hidden from our view, obscured by vast clouds of dust and gas that lie between us and the galactic center. These cosmic clouds block visible light much like fog blocks our view on Earth, making it impossible to see the core of our galaxy with ordinary optical telescopes. However, infrared light and radio waves can penetrate these veils, allowing astronomers to peer through the darkness and study the hidden heart of our galaxy. Fact 10. A supermassive giant at the core. At the very center of the Milky Way, approximately 26,000 light-years from Earth, lurks a supermassive black hole known as Sagittarius A*, pronounced Sagittarius A star. This cosmic monster contains the mass of about 4 million suns compressed into a region smaller than Mercury's orbit. Despite its enormous mass, this black hole is relatively quiet compared to those in other galaxies, gently feeding on gas and dust that ventures too close. Fact 11. Proving the invisible giant. For years, astronomers tracked individual stars orbiting near the galactic center, watching them whip around an invisible point at incredible speeds. Some of these stars complete their orbits in as little as 16 years, reaching velocities of several percent the speed of light. By carefully measuring these stellar dances, scientists proved that something massive and invisible must exist at that precise location. In 2020, this work earned Andrea Ghez and Reinhard Genzel the Nobel Prize in Physics. Fact 12. The first image of our central black hole. In May 2022, astronomers unveiled the first image of Sagittarius A*, showing a glowing ring of hot gas swirling around the dark shadow of the black hole itself. This image required combining observations from radio telescopes around the world, effectively creating a telescope the size of Earth. The glowing ring you see in the image isn't the black hole itself, but rather material heated to billions of degrees as it spirals toward the point of no return. Fact 13. The zone of intense gravity. Near the galactic center, the gravitational environment is extreme. Stars there must contend not only with the pull of the central black hole but also with the combined gravity of millions of other stars packed into a relatively small volume. Some stars venture so close to Sagittarius A* that they experience effects predicted by Einstein's theory of general relativity, with their light shifting to redder wavelengths as they climb out of the black hole's gravitational well. Fact 14. A mysterious past at the core. Evidence suggests that Sagittarius A* was once much more active than it is today. X-ray observations have revealed enormous structures extending thousands of light-years above and below the galactic plane, likely created by powerful outbursts from the central black hole millions of years ago. These echoes of past violence hint that our galactic center goes through cycles of quiet feeding and explosive activity. Fact 15. The nuclear star cluster. Surrounding Sagittarius A* is one of the densest concentrations of stars in the galaxy, called the nuclear star cluster. This region, spanning about 30 light-years across, contains roughly 25 million stars. If Earth were located in this stellar metropolis, our night sky would be ablaze with thousands of stars brighter than Venus, and there would be no true darkness, only a perpetual twilight created by countless nearby suns. Fact 16. Strange stars and strange orbits. Among the stars orbiting near Sagittarius A* are some truly peculiar objects. Astronomers have discovered what appear to be massive stars that shouldn't be able to exist so close to the black hole, as the extreme environment should have prevented their formation. These stars may have migrated inward from farther out in the galaxy, or they might have formed from the collision and merger of smaller stars in the dense stellar environment. Fact 17. The Central Molecular Zone. Surrounding the galactic center is a region called the Central Molecular Zone, containing millions of solar masses worth of dense molecular gas. This vast reservoir of star-forming material creates new stars at a prodigious rate, though many mysteries remain about how star formation proceeds in such an extreme environment. The gas in this region is heated, compressed, and stirred by stellar winds, supernova explosions, and the gravity of the black hole itself. Fact 18. Filaments of energy. Stretching through the region near the galactic center are dozens of mysterious radiofilaments, long thin structures of magnetized gas that can extend for hundreds of light years. These filaments, discovered in the 1980s, still puzzle astronomers. They appear to be shaped by powerful magnetic fields, but their exact origin and the mechanism that creates such organized structures in the chaotic environment near the galactic core remain subjects of ongoing research. Fact 19. Rivers of stars and gas. The Milky Way's most distinctive features are its spiral arms, vast structures that curve gracefully outward from the central bar like cosmic whirlpools frozen in time. Our galaxy has four major spiral arms: the Perseus arm, the Scutum Centaurus arm, the Sagittarius arm, and the Norma arm. These aren't rigid structures but rather density waves, regions where stars and gas bunch up temporarily before moving on, much like cars bunching up in traffic even as individual vehicles continue to flow. Fact 20. Our home in the Orion Spur. Between the major spiral arms lie smaller structures called spurs or feathers. Our solar system resides in one such feature called the Orion Arm or Orion Spur, a partial arm that connects the inner Sagittarius arm with the outer Perseus arm. This local arm is about 3,500 light-years across and 10,000 light-years long, containing some familiar stellar neighbors including the bright stars Sirius, Procyon, and the stars of Orion's belt. Fact 21. Stellar nurseries in the arms. The spiral arms are where most of the galaxy's star formation occurs. These regions contain vast clouds of molecular hydrogen, the raw material for making stars. When you look at the Milky Way's spiral arms in infrared or radio wavelengths, they light up with the warm glow of stellar nurseries, regions where gravity is slowly compressing gas clouds into new generations of stars. The spiral arms act as cosmic factories, taking in raw gas and producing stars. Fact 22. The architecture of density waves. The spiral arms aren't material structures in the way we usually think of them. Instead, they're density waves that rotate around the galaxy at a different speed than the stars themselves. Imagine a traffic jam on a highway. The jam itself moves slowly backward relative to the flow of traffic, even though individual cars are moving forward. Similarly, stars and gas clouds pass through the spiral arms, slowing down briefly as they encounter the increased density, then speeding up again as they emerge. Fact 23. Triggering star birth. As gas clouds enter a spiral arm, they experience increased pressure from the surrounding denser environment. This compression can trigger the collapse of gas clouds that were already teetering on the edge of forming stars. The spiral arms thus act as catalysts, encouraging star formation not by providing material but by squeezing existing clouds. This is why the arms appear bright and blue in photographs. They're filled with young, hot, massive stars that formed recently. Fact 24. The Perseus Arm's stellar riches. The Perseus Arm, one of the galaxy's major spiral arms, lies about 6,000 to 7,000 light-years from our solar system in the direction away from the galactic center. This arm contains some spectacular star-forming regions visible from Earth, including the famous double cluster in Perseus and parts of the Milky Way visible in the constellations Cassiopeia and Cepheus. If you've ever wondered where new stars are being born nearby, the Perseus Arm is one of the closest stellar maternity wards. Fact 25. The Scutum Centaurus Arm. On the opposite side of the galaxy from Perseus lies the Scutum Centaurus Arm, one of the galaxy's two major inner arms. This structure may actually be part of a long bar of stars and gas extending from the galactic center. The Scutum Centaurus Arm is home to some of the galaxy's most massive star-forming regions, including the Scutum Star Cloud, one of the densest visible concentrations of stars in the night sky from Earth's perspective. Fact 26. How we map the invisible. Mapping the Milky Way's spiral structure presents unique challenges because we're observing from within the disk, trying to discern the shape of something we're embedded in. It's like trying to map a forest while standing among the trees. Astronomers use various techniques to trace the arms, including measuring the distances to young star clusters, mapping the distribution of molecular gas clouds, and tracking radio emissions from different parts of the galaxy to build up a three-dimensional picture of our home. Fact 27. The spiral pattern persists. Despite individual stars constantly flowing through the spiral arms, the overall pattern remains remarkably stable over millions of years. This persistence occurs because the density waves that create the arms result from the gravitational interaction between the galaxy's stars and gas, creating a self-sustaining pattern. The spiral structure is continually regenerated by the same gravitational forces that created it initially, like a wave pattern on water that maintains its shape even as individual water molecules move. Fact 28. A census of stellar citizens. The Milky Way contains between 100 billion and 400 billion stars, though obtaining an exact count remains challenging. The vast majority of these stars are small, cool red dwarfs, stars that are much smaller and dimmer than our Sun. These stellar embers can burn for trillions of years, far longer than the current age of the universe, meaning that every red dwarf star that has ever formed is still shining today, slowly converting its hydrogen fuel into helium. Fact 29. The Sun is unusually large. Our Sun, which seems so ordinary to us, is actually larger and brighter than about 85 to 90% of all stars in the galaxy. Most stars are red dwarfs with masses between 8 and 50% of the Sun's mass, while stars much larger than the Sun are exceedingly rare. If you could randomly pick a star from the Milky Way, you'd most likely select a cool, dim red dwarf that would be nearly invisible to the naked eye from even modest distances. Fact 30. The brightest stars burn briefly. At the opposite extreme from red dwarfs are the massive blue giants and supergiants, stars that can exceed 100 times the Sun's mass. These cosmic beacons burn incredibly hot and bright, shining with the light of millions of suns. However, their brilliance comes at a cost. They consume their nuclear fuel so rapidly that they live for only a few million years before exploding as supernovae. Many of the brightest stars you see in the night sky are these young, massive stars, even though they represent only a tiny fraction of the galaxy's stellar population. Fact 31. Stellar diversity in the disk. The galactic disk contains stars of various ages and compositions. Younger stars, formed more recently from gas enriched by previous generations, contain higher abundances of elements heavier than hydrogen and helium. These elements, which astronomers call metals, give astronomers clues about stellar ages and formation history. The youngest, most metal-rich stars tend to be found closer to the galactic plane and in the spiral arms, while older, metal-poor stars wander in a thicker distribution above and below the main disk. Fact 32. The oldest stars in the halo. The spherical halo surrounding the galactic disk contains some of the Milky Way's oldest stars. Many formed over 13 billion years ago when the universe itself was young. These ancient stars are metal-poor, born from gas that had been processed through only a few generations of stars. Studying these stellar fossils provides windows into the early universe and the conditions present when our galaxy was first forming. Fact 33. Binary and multiple star systems. Many stars in the Milky Way don't shine alone. Astronomers estimate that at least half of all stars exist in binary or multiple star systems, gravitationally bound together and orbiting their common center of mass. Some systems contain two similar stars dancing around each other, while others consist of massive bright stars paired with tiny red dwarfs. In some cases, 3, 4, or even more stars are bound together in complex orbital arrangements that would make any planets in such systems experience wildly varying levels of starlight throughout their years. Fact 34. Variable stars pulse with light. Among the Milky Way stars are thousands of variables, stars whose brightness changes over time. Some variables pulsate rhythmically, expanding and contracting like beating hearts, while others erupt unpredictably or eclipse each other in binary systems. One particularly important type, the Cepheid variables, brighten and dim in cycles that relate directly to their intrinsic luminosity, making them cosmic standard candles that astronomers use to measure distances across the galaxy and beyond. Fact 35. White dwarfs and stellar retirement. When stars like our Sun exhaust their nuclear fuel, they don't simply vanish. Instead, they shed their outer layers into space and leave behind a dense stellar ember called a white dwarf, a compact object about the size of Earth but containing up to 1.4 times the mass of the Sun. The Milky Way contains billions of these stellar remnants, slowly cooling and fading over trillions of years. The white dwarf that our Sun will eventually become will continue shining dimly long after all human civilization has ended. Fact 36. Neutron stars and stellar compression. When stars more massive than about 8 solar masses explode as supernovae, they can leave behind even more extreme remnants, neutron stars. These objects pack about 1.4 solar masses into a sphere only about 20 kilometers in diameter, making them incredibly dense. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. Some neutron stars rotate rapidly and emit beams of radiation from their magnetic poles, appearing to pulse as they spin. We call these pulsars, and the Milky Way contains thousands of them. Fact 37. The space between stars. The vast spaces between stars aren't completely empty. Instead, they're filled with an extremely thin gas called the interstellar medium, along with microscopic dust grains and cosmic rays. On average, there's only about 1 atom per cubic centimeter in interstellar space, far better than any vacuum we can create on Earth. Yet because space is so vast, the total mass of this tenuous material equals billions of solar masses spread throughout the galaxy. Fact 38. Molecular clouds and star cradles. The densest parts of the interstellar medium are molecular clouds, vast regions where gas has cooled and condensed enough for atoms to bond into molecules. These clouds, composed primarily of molecular hydrogen along with traces of other compounds like carbon monoxide and ammonia, are where stars are born. The largest molecular clouds can contain millions of solar masses of material and span hundreds of light years, making them among the most massive structures in the galaxy. Fact 39. Dark nebulae and hidden wombs. Some molecular clouds are so dense with dust that they appear as dark patches against the backdrop of stars, blocking the light from objects behind them. These dark nebulae were once mistaken for regions where no stars existed, but we now know they're actually stellar nurseries. The darkness indicates the presence of dust grains, microscopic particles of carbon, silicon, and other elements that formed in the atmospheres of dying stars and were expelled into space. Fact 40. The Orion Molecular Cloud Complex. One of the most famous and closest major star-forming regions is the Orion Molecular Cloud Complex, located about 1,350 light-years from Earth. This vast structure contains enough material to form thousands of Sun-like stars and is currently doing exactly that. The beautiful Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, is just the visible tip of this enormous star factory, a small cavity in the molecular cloud where young stars have blown away some of the surrounding gas. Fact 41. Hot bubbles and supernova remnants. Interspersed with the cold molecular clouds are regions of extremely hot, thin gas heated to millions of degrees by supernova explosions and the powerful winds from massive stars. These hot bubbles can expand for thousands of light years, sweeping up cooler gas and creating shells and filaments. Our solar system actually resides within one such structure called the local bubble, a region of hot, low-density gas about 300 light-years across that was likely created by supernovae that exploded millions of years ago. Fact 42. Cosmic dust grains. The dust that pervades the interstellar medium consists of tiny solid particles, typically only a fraction of a micrometer in size, smaller than particles in cigarette smoke. These grains form in the cool atmospheres and stellar winds of evolved stars, particularly in the extended atmospheres of red giant stars. Each grain is made of materials like carbon, silicon, and various ices, and they play crucial roles in galactic chemistry by providing surfaces where atoms can meet and combine into molecules. Fact 43. How dust colors the galaxy. Interstellar dust doesn't just block light, it also colors it. Dust particles preferentially scatter and absorb blue light while allowing red light to pass through more easily, a process called interstellar reddening. This means that distant stars and galaxies appear redder than they actually are, much like how the sun appears red when seen through smoke or haze. Astronomers must account for this reddening when measuring the properties of distant objects and determining their true colors. Fact 44. Magnetic fields thread the galaxy. Permeating the interstellar medium are magnetic fields, invisible lines of force that influence the motion of charged particles and shape the structure of gas clouds. These galactic magnetic fields, though extraordinarily weak by terrestrial standards, extend across vast distances and play important roles in how gas clouds collapse to form stars and how cosmic rays propagate through the galaxy. The fields likely originated in the early galaxy and have been amplified and shaped by galactic rotation and stellar processes over billions of years. Fact 45. Cosmic rays and stellar radiation. High-energy particles called cosmic rays constantly zip through interstellar space, striking Earth's atmosphere by the billions every second. Most cosmic rays are protons accelerated to nearly the speed of light, likely by supernova explosions and other violent events. These particles carry tremendous energy and can penetrate deep into space, affecting gas clouds, damaging spacecraft electronics, and even potentially influencing the climate and evolution of life on planets. The Milky Way glows faintly in gamma rays produced when cosmic rays collide with interstellar gas. Fact 46. From cloud to star. Star formation begins when a portion of a molecular cloud becomes dense enough that its own gravity overcomes the internal gas pressure pushing outward. This can happen when clouds collide, when pressure waves from nearby supernova explosions compress the gas, or when clouds pass through spiral arms. Once gravity takes over, the cloud begins to collapse, fragmenting into smaller clumps that will each become individual stars or star systems. Fact 47. The protostar phase. As a collapsing gas clump shrinks, it heats up from the conversion of gravitational potential energy into thermal energy. The object at the center, called a protostar, grows hotter and denser as material continues to fall onto it. During this phase, which can last several 100,000 years, the protostar is still surrounded by the cocoon of gas and dust from which it's forming, making it invisible at optical wavelengths but bright in infrared light. Fact 48. Bipolar jets and stellar winds. Young protostars don't simply accrete material uniformly. Instead, they often launch powerful jets of material perpendicular to the disk of gas and dust swirling around them. These bipolar jets can extend for light years, creating beautiful bow shocks where they collide with surrounding gas. The jets help remove excess angular momentum from the system, allowing material to continue falling onto the growing star. The exact mechanism that creates these jets remains an active area of research. Fact 49. The birth of nuclear fusion. When the protostar's core reaches about 10 million degrees Celsius, hydrogen nuclei begin to fuse into helium, releasing tremendous energy through Einstein's famous equation E=mc². This moment marks the birth of a true star. The energy released by fusion creates an outward pressure that balances the inward pull of gravity, allowing the star to reach a stable equilibrium. This balance will be maintained for most of the star's life, whether that's billions of years for a small star or just millions for a massive one. Fact 50. Stellar clusters and sibling stars. Stars rarely form in isolation. Instead, molecular clouds fragment into hundreds or thousands of stellar cores, creating entire clusters of sibling stars born from the same cloud at roughly the same time. These open clusters, such as the Pleiades or the Hyades, contain stars that share similar ages and chemical compositions. Over time, gravitational interactions and encounters with molecular clouds gradually disperse these clusters, scattering their member stars throughout the galaxy. Fact 51. The initial mass function. The process of star formation seems to favor creating large numbers of small stars and relatively few massive ones, following a pattern astronomers call the initial mass function. For every star of 10 solar masses that forms, hundreds of solar mass stars and thousands of red dwarfs are born. This distribution has profound implications for the galaxy because massive stars live briefly and die violently, enriching the interstellar medium with heavy elements, while low-mass stars burn slowly and steadily for eons. Fact 52. Planet formation alongside stars. The same disk of gas and dust that feeds a growing protostar also provides the raw material for planet formation. In the cooler regions of the disk, dust grains stick together through electrostatic forces, gradually building larger and larger objects. These planetesimals, ranging from meters to kilometers in size, continue to collide and merge, eventually forming rocky planets close to the star and gas giants farther out where ices can exist. The Milky Way likely contains hundreds of billions of planets. Fact 53. Massive star formation mysteries. While astronomers have a good understanding of how stars like the Sun form, the formation of truly massive stars, those exceeding 20 or 30 solar masses, remains more mysterious. The radiation pressure from these growing behemoths should be so strong that it pushes away infalling material, theoretically preventing them from accumulating enough mass. Yet massive stars clearly exist. Current theories suggest they may form through the merger of smaller stars or by accreting material through channels in their surrounding disks where radiation can escape. Fact 54. The star formation rate. The Milky Way currently forms about 1 to 3 solar masses worth of new stars each year, a relatively modest rate compared to some other galaxies. This rate has declined over the galaxy's history as the supply of fresh gas available for star formation has gradually been consumed. The spiral arms host most of the current star formation, with massive molecular clouds like those in Orion, Carina, and Cygnus serving as the galaxy's most productive stellar factories. Fact 55. When hydrogen runs out. Eventually, every star exhausts the hydrogen fuel in its core. For stars like the Sun, this moment comes after about 10 billion years of steady burning. When the core hydrogen is depleted, fusion stops temporarily, and the core begins to contract under gravity, heating up. This increased temperature causes hydrogen in a shell around the core to begin fusing, and the energy from this shell burning causes the star's outer layers to expand dramatically, transforming the star into a red giant. Fact 56. The red giant phase. During the red giant phase, a star swells to enormous size while its surface cools and reddens. A Sun-like star will expand to roughly the orbit of Earth, engulfing the inner planets. Despite the cooler surface temperature, the total energy output increases dramatically because of the star's vastly increased surface area. This phase represents the beginning of the end for Sun-like stars, a transition that will last several 100 million years before the final transformation begins. Fact 57. Helium burning and carbon creation. As the red giant's core continues to contract, it eventually becomes hot enough, about 100 million degrees, to fuse helium into carbon through a process called the triple alpha process. This ignition happens suddenly in stars like the Sun, in an event called the helium flash, but the star's outer layers remain mostly unaffected. More massive stars can proceed to fuse carbon into heavier elements like oxygen, neon, and eventually iron, but Sun-like stars lack the mass to achieve these higher temperatures. Fact 58. Planetary nebulae in beautiful death. In the final stages, red giant stars begin to pulsate and shed their outer layers into space through powerful stellar winds. These expelled shells of gas, illuminated by ultraviolet radiation from the hot stellar core left behind, create planetary nebulae, some of the most beautiful objects in the galaxy. Despite their name, these nebulae have nothing to do with planets. Early astronomers simply thought they resembled planetary disks through primitive telescopes. Each planetary nebula is a fleeting monument to a dead star, lasting only tens of thousands of years before dissipating into the interstellar medium. Fact 59. Enriching the galaxy with heavy elements. The gas expelled by dying stars carries with it the elements forged in their interiors: carbon, nitrogen, oxygen, and many others. These elements, created from the simple hydrogen and helium the star was born with, enrich the interstellar medium, providing the raw materials for the next generation of stars and planets. The atoms in your body, the calcium in your bones, the iron in your blood, the carbon in your DNA, were all created in the interiors of stars that lived and died before our sun was born. Fact 60. Supernova explosions. Stars more massive than about 8 solar masses meet a far more violent end. After fusing elements up to iron in their cores, they can go no further. Iron fusion consumes energy rather than releasing it. Without energy to support it against gravity, the core collapses catastrophically in a fraction of a second. The outer layers of the star then crash inward and rebound off the incredibly dense core, creating a shock wave that tears the star apart in a supernova explosion that briefly outshines the entire galaxy. Fact 61. Creating the heaviest elements. The extreme conditions inside a supernova explosion, tremendous temperatures, densities, and neutron fluxes, allow the creation of elements heavier than iron. Gold, platinum, uranium, and other heavy elements are forged in these violent deaths and scattered into space by the explosion. Recent discoveries suggest that collisions between neutron stars may be equally important for producing these heavy elements. Every gold atom in every ring, every coin, was created in such a cataclysm somewhere in the galaxy's past. Fact 62. Supernova remnants light up the galaxy. The expanding debris from a supernova creates a supernova remnant, a shell of hot gas expanding into the surrounding interstellar medium at thousands of kilometers per second. These remnants can remain visible for tens of thousands of years, creating beautiful and complex structures as they interact with clouds of gas and magnetic fields. The Crab Nebula in Taurus, the remnant of a supernova observed by Chinese astronomers in 1054 CE, remains one of the most studied objects in the sky. Fact 63. Triggering new star formation. Ironically, the violent death of massive stars can trigger the birth of new ones. When a supernova shock wave slams into a nearby molecular cloud, it compresses the gas, potentially triggering gravitational collapse and star formation. In this way, stellar death and birth are intimately connected in a cosmic cycle. The Sun itself may have been born in a molecular cloud compressed by a nearby supernova explosion, with the shock wave not only triggering its formation but also delivering fresh heavy elements to be incorporated into our solar system. Segment 8. The Galactic Halo, 70 to 80 minutes. Fact 64. A spherical halo of stars. Beyond the flat disk of the Milky Way lies the stellar halo, a roughly spherical distribution of stars and star clusters that extends far above and below the galactic plane. This halo is much less populated than the disk, containing perhaps 1% of the galaxy's stars, but it extends much farther into space, reaching out 100,000 to 200,000 light-years from the galactic center. The halo stars follow orbits highly inclined to the galactic plane, plunging through the disk and out the other side in their long journeys around the galaxy. Fact 65. Globular clusters in the halo. Scattered throughout the galactic halo are approximately 150 known globular clusters, ancient spherical collections of hundreds of thousands to millions of stars bound together by gravity. These clusters are relics from the early universe, formed over 13 billion years ago when the galaxy was young. Looking at a globular cluster like Omega Centauri or M13 is like gazing back in time to see stars that have been shining since the first epochs of cosmic history. Fact 66. The oldest stars we know. The stars and globular clusters in the halo are among the oldest objects in the galaxy, many formed within the first billion years after the Big Bang. These ancient stars are metal-poor, containing only trace amounts of elements heavier than helium because they formed from gas that had been processed through only one or two previous generations of stars. By studying these stellar ancients, astronomers can probe the conditions in the early universe and learn how the first generations of stars enriched their environment. Fact 67. RR Lyrae variable stars. Globular clusters often contain pulsating variable stars called RR Lyrae variables, which brighten and dim with periods typically less than a day. Like Cepheid variables, these stars have a relationship between their pulsation period and luminosity, making them useful distance indicators. Because RR Lyrae stars are found in globular clusters of known age, they help astronomers calibrate the cosmic distance scale and determine the ages of ancient stellar populations throughout the galaxy. Fact 68. Stellar streams in the halo. Recent surveys have revealed that the galactic halo is crisscrossed by streams of stars, the remnants of smaller satellite galaxies and star clusters that were torn apart by the Milky Way's gravity. These stellar streams trace out the orbital paths of their progenitors, creating arcs and ribbons across the sky. The Sagittarius stream, for example, wraps completely around the Milky Way, marking the tidal disruption of the Sagittarius dwarf elliptical galaxy as it orbits our much larger galaxy. Fact 69. Dark matter in the halo. The stellar halo is embedded within a much larger dark matter halo, an invisible sphere of mysterious matter that extends perhaps 600,000 light-years from the galactic center. This dark matter, which doesn't emit, absorb, or reflect light, can only be detected through its gravitational influence on visible matter. The dark matter halo contains roughly 10 times more mass than all the stars, gas, and dust in the galaxy combined, making it the dominant component of the Milky Way's total mass. Fact 70. Satellite galaxies in orbit. The Milky Way doesn't drift through space alone. It's attended by dozens of satellite galaxies, smaller galaxies gravitationally bound to our own and orbiting around it. The largest and most famous of these are the Large and Small Magellanic Clouds, irregular dwarf galaxies visible from the southern hemisphere as fuzzy patches of light. These cosmic companions contain billions of stars of their own and are slowly being tidally disrupted by the Milky Way's gravity. Fact 71. The Large Magellanic Cloud. The Large Magellanic Cloud lies about 160,000 light-years away, making it one of the closest galaxies to the Milky Way. This dwarf irregular galaxy contains roughly 30 billion stars and is currently undergoing active star formation, particularly in a region called the Tarantula Nebula, one of the most luminous star-forming regions in the local group. The Large Magellanic Cloud was the site of supernova 1987A, the closest observed supernova to Earth in nearly 400 years. Fact 72. Andromeda, our sibling galaxy. At a distance of about 2.5 million light-years, the Andromeda Galaxy is the nearest large spiral galaxy to the Milky Way and the most distant object visible to the naked eye. Andromeda is similar in structure to our galaxy but contains roughly twice as many stars, making it the largest member of our local group of galaxies. When you look at Andromeda on a dark night, you're seeing light that has been traveling through space for 2.5 million years, light that left the galaxy when early human ancestors were just learning to use stone tools. Fact 73. The coming collision. The Milky Way and Andromeda are not stationary relative to each other. They're actually approaching at about 110 kilometers per second, and in approximately 4 to 5 billion years, these two great spiral galaxies will collide. This collision won't be a destructive crash but rather a gravitational ballet lasting billions of years as the galaxies pass through each other, merge, and eventually settle into a single giant elliptical galaxy. Despite the collision, actual stellar collisions will be extraordinarily rare due to the vast distances between stars. Fact 74. The local group of galaxies. The Milky Way, Andromeda, and their various satellite galaxies are all members of a gravitationally bound association called the local group, which contains more than 80 galaxies spread across roughly 10 million light-years of space. Most of these galaxies are small, dim dwarf galaxies, many discovered only in recent years through sensitive surveys. The local group is our cosmic neighborhood, the immediate family of galaxies among which the Milky Way resides. Fact 75. The Triangulum Galaxy. The third largest member of the local group is the Triangulum Galaxy, a spiral galaxy about 3 million light-years away containing roughly 40 billion stars. Triangulum is notable for its open spiral structure and active star formation. Unlike the Milky Way and Andromeda, which are roughly the same age as the universe, Triangulum may have formed somewhat later, and it shows more ongoing star formation activity, giving astronomers insights into how galaxies evolve and change over cosmic time. Fact 76. Dwarf spheroidal companions. Most of the Milky Way's satellite galaxies are extremely faint dwarf spheroidal galaxies, collections of typically a few million stars spread diffusely across thousands of light-years. These tiny galaxies are so dim that many remained undiscovered until recent decades when sensitive surveys revealed them. Galaxies like Sculptor, Fornax, and Leo I contain old stellar populations and are being slowly torn apart by the Milky Way's tidal forces as they orbit our much larger galaxy. Fact 77. The Sagittarius Dwarf Elliptical Galaxy. One of the Milky Way's closest satellite galaxies is the Sagittarius Dwarf Elliptical Galaxy, discovered only in 1994 despite lying a mere 70,000 light-years from the galactic center. This galaxy had gone unnoticed because it lies on the far side of the Milky Way's bulge from our perspective, hidden behind the dense star fields of the galactic center. Sagittarius Dwarf is currently being torn apart by tidal forces, with streams of its stars wrapping multiple times around our galaxy. Fact 78. Galactic cannibalism. The Milky Way has grown over its lifetime partly through mergers with smaller galaxies, a process sometimes called galactic cannibalism. The stellar streams and unusual star clusters we observe today are the digested remains of ancient dwarf galaxies that were consumed by our galaxy billions of years ago. Even now, this process continues as satellite galaxies like Sagittarius Dwarf are gradually torn apart and incorporated into the Milky Way's halo, adding their stars to our galaxy's collection. Fact 79. Birth of our galaxy. The Milky Way began forming approximately 13.6 billion years ago, only a few 100 million years after the Big Bang itself. The earliest components were likely globular clusters and metal-poor halo stars that formed from relatively pristine primordial gas. Over time, these early structures merged and coalesced, gradually building up the protogalactic cloud that would eventually settle into the rotating disk we see today. Fact 80. The thick disk and ancient mergers. Between the thin disk where most stars reside and the stellar halo lies an intermediate structure called the thick disk, containing older stars with different chemical compositions and kinematics than the thin disk population. This thick disk likely formed through early mergers with satellite galaxies about 10 billion years ago, when the Milky Way was still young and actively incorporating smaller structures. These ancient collisions stirred up the early disk, heating it and puffing it up into the thicker structure we observe today. Fact 81. The Gaia-Enceladus merger. Around 10 billion years ago, the young Milky Way experienced a major merger with a galaxy about 1/4 its mass, an event now called the Gaia-Enceladus merger after being discovered through data from the Gaia Space Telescope. This collision dramatically affected the galaxy's structure, contributing stars to the halo and thick disk and possibly triggering a burst of star formation. The remnants of this ancient galaxy can still be identified today as a population of stars with distinctive orbital characteristics and chemical compositions. Fact 82. The formation of the bar. The prominent bar structure at the Milky Way's center formed relatively late in the galaxy's history, perhaps only 5 to 10 billion years ago. This bar likely arose from gravitational instabilities in the disk as it accumulated mass and evolved. Once formed, the bar dramatically affected the galaxy's subsequent evolution, funneling gas toward the central regions, influencing the spiral arm structure, and creating the complex orbital patterns we observe in the inner galaxy today. Fact 83. Variations in star formation history. The Milky Way star formation rate has varied dramatically over cosmic time. The early galaxy experienced vigorous star formation as abundant primordial gas collapsed into the first stellar generations. The rate then declined as gas was consumed, but it increased again during merger events that brought fresh gas into the system. Today's relatively modest star formation rate represents a quieter phase in the galaxy's evolution, though star formation continues steadily in spiral arms and molecular clouds. Fact 84. Chemical evolution over time. Each generation of stars has enriched the interstellar medium with heavier elements, leading to a gradual increase in metallicity over the galaxy's history. The oldest stars in the halo contain less than 1% of the Sun's iron abundance, while young stars forming today can have metallicities exceeding solar values. This chemical evolution is written in stellar spectra, allowing astronomers to use stellar chemistry as a cosmic clock, determining relative ages based on elemental abundances. Fact 85. Past supernova events. Throughout its history, the Milky Way has experienced countless supernova explosions, each briefly illuminating the galaxy and enriching the interstellar medium. Some of these explosions occurred close enough to Earth to have potentially affected our planet. Isotopic anomalies found in ancient ocean sediments suggest nearby supernovae within the last few million years, and some scientists speculate that such events could have influenced Earth's climate or even the evolution of life. Fact 86. The future of star formation. As the Milky Way continues to age, its star formation rate will gradually decline. The galaxy is running out of the dense molecular gas needed to form new stars. An infall of fresh gas from outside cannot keep pace with the rate of consumption. In perhaps a few billion years, star formation will slow to a trickle, and the galaxy will gradually transition from a spiral with bright blue arms to a redder, quieter system dominated by older stars. Fact 87. The Milky Way's ultimate fate. The collision with Andromeda in 4 to 5 billion years will dramatically reshape the Milky Way. The two galaxies will pass through each other, fall back together, and eventually merge into a single giant elliptical galaxy that astronomers have playfully nicknamed Milkomeda or Milkdromeda. This new galaxy will likely have little disk structure and minimal star formation, representing a final, quiescent state. Our Sun and Solar System will likely survive this cosmic collision, but they'll end up in a very different galactic environment than where they started. Fact 88. Early observations in mythology. Ancient cultures around the world observed the Milky Way and wove it into their mythologies and cosmologies. The Greeks saw spilled milk from the goddess Hera, Chinese astronomers called it the Silver River, Norse mythology described it as a path to Valhalla, and many Native American tribes saw it as a road traveled by spirits. These stories reflected humanity's earliest attempts to understand the glowing band crossing the night sky, long before we knew what stars truly were. Fact 89. Galileo's first telescopic views. In 1610, Galileo turned his primitive telescope toward the Milky Way and discovered that the glowing band resolved into countless individual stars, too numerous to count. This observation was revolutionary, demonstrating that the Milky Way wasn't a continuous glow but rather a vast collection of distant suns. Galileo's discovery represented humanity's first step toward understanding the true nature and scale of our galaxy. Fact 90. Herschel maps the galaxy. In the late 18th century, William Herschel attempted to map the Milky Way by systematically counting stars in different directions. He concluded that the galaxy had a disk-like shape with the Sun near its center. While Herschel's general conclusion about the disk structure was correct, he didn't realize that interstellar dust was obscuring his view of more distant regions, leading him to underestimate the galaxy's size and misplace the Sun's position within it. Fact 91. The Great Debate. In 1920, astronomers Harlow Shapley and Heber Curtis engaged in a famous debate about the scale of the galaxy and the nature of spiral nebulae. Shapley argued correctly that the Milky Way was much larger than previously thought and that the Sun was far from its center, but incorrectly believed spiral nebulae were part of our galaxy. Curtis argued the opposite on both counts. The debate highlighted fundamental questions about cosmic scale that would only be resolved in the following years. Fact 92. Discovering our place. In the 1920s, observations of variable stars and globular clusters by Harlow Shapley revealed that these clusters formed a spherical halo centered far from the Sun's location, demonstrating that we weren't at the galaxy's center but rather in its outskirts. This was a profound shift in perspective, displacing humanity further from any special cosmic location, first from the center of the solar system, then from the center of the galaxy itself. Fact 93. Radio waves penetrate the dust. The development of radio astronomy in the mid-20th century revolutionized our understanding of the Milky Way. Radio waves can penetrate the dust clouds that block visible light, allowing astronomers to map the distribution of hydrogen gas throughout the entire galaxy for the first time. These observations revealed the spiral arm structure and provided the first complete picture of our galaxy's shape and size. Fact 94. Infrared eyes see through darkness. Infrared observations, particularly from space-based observatories like the Spitzer Space Telescope and ESA's Herschel Space Observatory, have revealed the cooler components of the galaxy invisible to optical telescopes. Infrared light penetrates dust clouds and detects the warm glow from star-forming regions, allowing astronomers to study stellar nurseries hidden in molecular clouds and to map the distribution of dust throughout the galactic disk. Fact 95. The Gaia missions revolution. Launched by the European Space Agency in 2013, the Gaia spacecraft is creating the most detailed three-dimensional map of the Milky Way ever made. By precisely measuring the positions, distances, and motions of over 1 billion stars, Gaia is revealing the galaxy's structure, history, and dynamics in unprecedented detail. Discoveries from Gaia have rewritten our understanding of the Milky Way's past, revealing ancient merger events and the complex motions of stellar populations. Fact 96. Hunting for exoplanets. Missions like Kepler and TESS have revealed that planets are remarkably common in the Milky Way, with most stars hosting at least one planet and many hosting entire planetary systems. These discoveries have fundamentally changed our perspective on the galaxy, transforming it from a collection of stars to a vast expanse filled with worlds of every imaginable type. The Milky Way may contain hundreds of billions of planets, many of them potentially capable of supporting life. Fact 97. The galactic habitable zone. Not all locations in the Milky Way are equally conducive to life. The inner regions near the galactic center experience frequent supernova explosions and intense radiation that could sterilize planetary surfaces. The outer regions lack sufficient heavy elements needed to form rocky planets. Between these extremes lies the galactic habitable zone, a ring-shaped region including our solar system's location where conditions are more favorable for the development of life. Fact 98. The building blocks of life. The molecular clouds where stars and planets form contain complex organic molecules, the building blocks of life as we know it. Radio telescopes have detected hundreds of different molecules in interstellar space, including amino acids and sugar molecules. These molecules form on dust grain surfaces and in gas phase reactions, then get incorporated into forming planetary systems. Life on Earth may have begun with complex organic molecules delivered by comets and meteorites that formed in the primordial solar nebula. Fact 99. The search for intelligent life. For decades, scientists have searched for signs of intelligent life in the Milky Way through programs like SETI, the search for extraterrestrial intelligence. Radio telescopes scan the sky for artificial signals from technological civilizations, while some researchers look for optical laser pulses or other signs of advanced technology. So far, these searches have found nothing definitive, leading to questions about how common intelligent life might be and whether technological civilizations tend to be long-lived or fleeting. Fact 100. Our cosmic context. As we drift towards sleep, consider that everything you are, everything you've ever known, everyone who has ever lived, every human thought, achievement, and dream has occurred in one tiny corner of one galaxy among billions. The Milky Way is vast beyond human comprehension, ancient beyond human timescales, yet it's our home. We are, quite literally, made of stardust, atoms forged in the hearts of stars that lived and died before our sun was born. The galaxy is not separate from us, we are part of it, temporary patterns in the cosmic flow, conscious for a brief moment as the universe contemplates itself. Every breath you take contains atoms that have cycled through countless stars across billions of years. You are the Milky Way's way of knowing itself, of experiencing wonder, of asking questions about its own nature. And with that comforting thought, knowing you're part of something so magnificent and eternal, you can rest peacefully beneath the stars.